So we're in the middle of proving this wonderful theorem. That basically says that we understand exactly what the finite Coxeter groups are. And they're given by this list of Coxeter diagrams. So the way we're doing this, where did my note go? Oh, here. The way we're doing this is by this fact that the Coxeter group is finite if and only if this matrix that we associate to it, which I'm going to call 2A gamma, is positive definite. And we said that there's two ways of saying what this means. One is that x transpose AX is positive for all non-zero x. And another way of saying this is that all the principal minors of this matrix are positive, right? So let's see, what else do I need to remind you of to continue this discussion? Maybe I'll remind you that I was using this notation d of gamma to be the determinant of the matrix 2A gamma, where we actually computed these numbers here. And so let me remind you what they were. So we proved that d of an was, where did it go? N plus 1. D of bn was 2. D of dn was 4. These guys were 3, 2, and 1. F4 was 1. H3 was 3 minus square root of 5. This was 7 minus 3 square root of 5 over 2. And this was 4 sine squared of pi over m. Okay. And by proving that all of these numbers were positive, we proved that all of these Coxeter groups that I'm defining in this way are actually finite. Okay? And so we're in the middle of the other direction, which is now to show that if we have a finite Coxeter group, then it has to be one of these guys. So maybe one thing that we should remind ourselves is that when just some values that are going to keep coming up. So for example, we know that in the diagonal of the matrix, we always see 2's, and this is where Mij is equal to 2. When Mij is 3, we see negative 1's. When Mij is 4, we get minus 2 cosine of pi over 4. And, well, this is root 2 minus root 2, etc. And these values will come up, so I want to record them there. Okay. So we're returning now and saying if W is finite, irreducible, then gamma is in this list. Okay. And we started by proving last time. I said I was going to do this in several steps. Basically, we're going to start with a graph gamma. We're assuming that the Coxeter group is finite irreducible, and I'm going to step by step get to the fact that it's one of these guys. And so the first thing we proved last time is that we're not going to see any labels that are infinity. As soon as you see an infinite label, then you know that this thing is finite. Okay? Now, the next thing I'm going to prove is that if W is finitely reducible, then gamma has no cycles. Okay? I think I have this wrong, actually. When Mij is 1 is when I and j are equal to each other, and in this case I get 2. But remember that most of the entries in these matrices are 0, which is when Mij is equal to 2. Okay. So let's suppose that gamma actually had a cycle. So suppose gamma looks like this, and then maybe it has other things. I don't know, anything like that. Here's gamma, and there's labels that are finite numbers. Okay, so now what I want to do is say, okay, well, if this graph gives me a finite Coxeter group, then also this graph is going to give me a finite Coxeter group, right? If I just ignore everything but the cycle, the reason being that I'm just paying attention to these vertices, and they form a parabolic subgroup of this guy. So if my group is finite, its subgroup is also going to be finite. And therefore, I might as well just forget that this exists. Okay? And let me just pay attention to this part. Okay? This thing gives me a finite Coxeter group. Okay? Now, what does that mean? That means that the matrix that we get is going to be positive definite. This is a positive definite matrix. And what does it look like? Well, we know that our matrices always have 2's on the diagonal. Okay. Now, if I label these vertices 1, 2, let me label them by letters better. So A, B, C, D, E, F. And so these are the labels also of the rows and columns of my matrix. Now, the point is that A is only connected to B and F, and it's not connected to C, D, and E, which means that AC, AD, and AE are 2's, which give me 0's in the matrix. So my point is basically that this matrix is almost all 0's, but between A and B I have something, between A and F I have something. Okay? Between B and C I have some number, between C and D, between D and E, etc. So these stars are actual numbers that might be something interesting. Between A and F, I might have something, but everything else is 0. This is all 0's and 0's. Here I'm assuming that the cycle is induced in the sense that I don't have any edges connecting, for example, B and E. If I had that, then I would just consider the smaller cycle. I just consider the smallest cycle around, and that'll do. So this is supposed to be a positive definite matrix. Okay? But I'm going to show to you that it isn't. Why? Well, if it's positive definite, then I can plug in any x into here, and I should be getting some positive number. And the x that I would like to plug in is the simplest one that I can think of, which is the all ones vector. So this should give me a positive number, right? But now if you see what happens when you multiply some matrix by the all ones vector like this, what you are going to get is just the sum of the rows of this matrix. If you multiply a matrix by the all ones vector horizontally, what you're going to get is the sum of the columns of the matrix. So if you multiply on the right by this, on the left by this, and you do it, you're going to see that what you get is simply the sum of all the numbers in the matrix. Okay? So the sum of all the entries in the matrix is supposed to be positive. Okay? What is that sum? Well, I have two, let's say, n times, where n is the number of vertices on this cycle. plus some sum of things. Okay, how many of things do I have? How many of these things do I have? Well, you see, I have 2 stars in each row, so there's 2 n terms. Right? Two n numbers. But the thing is that I want to pay attention to what these numbers are. Because what are these numbers? Well, they look like minus 2 cosine of pi over m something. I plus 1. Okay. Now, the thing is that I plus 1 is at least 3, right? Why is that? Well, because there's an edge between I and I plus 1, okay? So this is cosine of pi over 3 or something smaller, which means that this number, without the minus sign, is greater than or equal to 2 cosine of pi over 3. With the minus sign, it's less than or equal to minus 2 cosine of pi over 3. But what's this? This is minus 1. Okay? And so what do I have? I have 2n plus a sum of 2n numbers, each one of which is less than or equal to negative 1. And that answer is not going to be positive. Okay? So that's a contradiction. And so that proves to me that gamma has no cycles. Okay? So that's good. Now we know why we only see trees here. Okay? Any questions about that argument? It's good? Okay. So let's continue. Now I would like to explain why it is that actually not only do I not see infinities, but actually I don't see very big numbers here anywhere. Okay? And maybe this shouldn't be too surprising because a big number means 2 generators such that Si, Sj has a very high order and that produces a lot of elements, okay, in the group. But so now what I want to do is restrict the numbers and say not only that I don't have infinities, but I want to say more. So the next thing I want to prove is this. Gamma has at most one edge labeled with a number bigger than 3. Okay? In these pictures, you never see 2 different labels bigger than 3. So why is that? Well, suppose that you did have 2 things bigger than 3. 2 edges labeled bigger than 3. Okay, so here's my graph. Somewhere in the graph, I have some edge labeled P. Somewhere in the graph, I have some edge labeled Q, and I don't know what the rest of the graph is, except that I'm assuming that my group is irreducible, which means that my graph is connected, and that means that there must be some path from here to here. Okay, so I just take that path. Okay, so I have something like this, and I'm going to focus on this part. Okay, and of course, my graph could have other things. Right? It could be well, I know it has no cycles now, but it could be some bigger graph. I'm going to make the same argument as before. I'm going to say if my bigger graph produces a finite Coxeter group, then this is a parabolic subgroup, so that's also finite. And then I make a very similar argument. I say, okay, well, this gives me some matrix that is positive definite. And what does that matrix look like? Let me call this A, B, C up to, I don't know, F. So I have, well, I'm going to need a bit more space. So I know I have 2's all over the diagonal. I know I'm going to have a whole lot of zeros. The only things that might not be 0 are the entries connecting A and B and C, etc., until E and F. Okay. here I have these entries between A and F that might be non-zero, but that's because A and F are connected here, A and F are not connected here. So these are the only things that are non-zero. Okay? And I make the same argument, which is that if I add everything, I better get a positive number. Okay? Now, let me make a couple of assumptions. If there was a number along this path other than a 3, for example, if here I have an r which is bigger than 3, then I could just have done this for the smaller path. Okay? In other words, what I can assume is that all of these guys are labeled 3. And if I assume that all of these guys are labeled 3, then basically I know that when we have edges labeled 3 there, what we see is negative 1s here. So negative 1, negative 1, negative 1, negative 1. And now I add up all of these numbers. So I have, again, 2 n times. Then I have minus 1 how many times? Well, I guess there's 2 n minus 2 times. Right? Yeah. And then I have to add up these 4 entries, which actually I know what they are, right? Because they're just cosine of pi over p twice. Well, twice minus 2 cosine of pi over p, and twice minus 2 cosine of pi over q. And this number should be positive. Okay? But I compute this number, so I get 4 minus 4 cosine pi over p minus 4 cosine pi over q is positive. Okay? But again, what's the point? Well, the point is that p is bigger than or equal to 4, right? So cosine of pi over p is less than or equal to cosine of pi over 4, which is square root of 2 over 2, right? And the same for q. So if I take minus 4 cosine of pi over p, this is going to be less than or equal to minus 2 root 2. Okay? So that means that this is less than or equal to 4 minus 2 root 2 minus 2 root 2. And so what I just proved for you is that 1 is bigger than or equal to square root of 2. So if I prove that, that means that something must have gone wrong along the way, which was the original assumption. And so that proves my statement that gamma has at most one edge labeled bigger than 3. Okay? So that's good. We're getting to know a lot about this graph. Okay? Okay. So next thing, if gamma has an edge bigger than 3, then it is a path. You see that there, all these things that have numbers on them are paths. Okay? So how do I do that? Well, suppose not again. So suppose that we have some edge bigger than 3, and suppose that it's not a path. Now, if it's not a path, but it is a tree, that means that there must be somewhere that it branches. So there must be some place where it looks like this, because otherwise it would be a path. And again, this is a connected graph, so I can find something like this as a subgraph, and this gives me a positive definite matrix. Okay. So what am I going to do now? I'm going to compute. So you see, so far in my arguments, I use the first characterization of positive definiteness, but I'm going to use the second characterization by determinant. So given that this is positive definite, I'm going to compute its determinant, and it should be a positive number. Okay? So what's the determinant of something like this? Well, let me remind you of a lemma that we proved last time, which was our main tool for computing these numbers. And it said this. It said that if you have a graph gamma, and you have, basically, this is going to be a way of peeling off one vertex. Okay? So we said if gamma looks like this, where this guy is connected only to this guy is connected to other things, and then here you have some other graph, then you can compute the determinant of gamma in terms of the gamma prime you obtain by removing this leaf and just keeping this part of the graph, and the gamma double prime that you obtain by removing this whole claw and just leaving this part of the graph. And the formula was that d of gamma is equal to 2d of gamma prime minus, let me sure I get this right, 4 cosine squared of pi over n, the determinant of gamma double prime. Okay? Why is this a very good tool? Well, it's a very good tool because here we have a graph where we don't know its determinant, but the only reason we don't know it is because of this label p. But if you forget about this label p, then all of a sudden we get a graph that we know the determinant of. So we can use this recurrence to say exactly what this is. Okay? 2 times determinant of erasing this thing. And so we're going to get the picture for d n minus 1 if there's n vertices here. Minus 4 cosine squared of pi over p times the determinant of what we get if we also remove this guy, and now we get this picture, which is the picture of dn minus 2. Okay. But we know that the dn has determinant 4 for any value of n, so this is just 8 minus 16 cosine squared of pi over p. And again, we're going to make this estimate that the cosine of pi over p is at most the square root of 2 over 2. So when I square it, it's going to be at most a half. So we get 8 minus 16 over 2, which is 0. Okay. And so that proves to me that this determinant is not positive, which means that I can't have something like this. So that means that gamma, well, that means that this statement D is true. Okay. So let's see where we are. First of all, we have no infinite edges. Second of all, we have no cycles, which means that we're dealing with trees only. Let me keep these statements up and erase the proof so that we can keep track of where we are. So the third statement was this one. I have at most one strange edge that is labeled by something bigger than 3. And the next statement is that if I have such an edge, then I'm just a path. So for example, I mean, what can I already conclude? I can already conclude that if my graph has edges labeled something bigger than 3, then I know exactly what they look like. They're a path. So let me summarize this by saying if I have an edge bigger than 3, then I look like this. And I'm finite. So if I'm finite and I have an edge bigger than 3, then I must look like just a path like this. Something like that. Right? Let's call this M since that's what we have been calling it all the time. And that really narrows down very much what these things can look like. So maybe this is well, this summarizes C and D. So I can just erase C and D. Okay. Now the next thing I would like to do then, I mean, at this point you see, the thing is that the way we proved that those guys are finite was by computing the determinants, and they were a nice enough family that we could compute this explicitly. Now I think you will believe me that if I gave you as a homework to compute the determinant for something like this, then you could do it also by the same recursive thing, because these things are simple enough that if you knock off one edge, then it still belongs to this family, and so you get some similar recursion. Okay? So here we're at a manageable spot where we'll be able to deal with this. Okay? What we don't know yet is how to deal with things that only have 3s. Those we don't know a lot about, but so let's narrow those down by proving the following. Let's prove that no matter what, if I have only 3s, still I'm only going to have at most one branching point. Gamma has at most one branching point. Okay. How do I prove this? Well, again, suppose not. Suppose I have 2 branching points like this, and because the graph is connected, that means that I can assume that I have something like this in my graph. I can also assume that these guys are all 3s, because if there was a number bigger than 3, then I wouldn't be finite because of this. Right? And so then what I have to do is simply compute the determinant of this thing. So what is the determinant of this? Well, again, this is easy at this point because I can just knock off this one guy and apply this recursion. So it tells me 2 times determinant of, forgetting about this edge, and so I get the picture for dn minus 1, minus 4 cosine squared of pi over m, which when m is 3 is just 1. And then the result of knocking off not only the edge but also the vertex. So now my graph looks like this, which means that I have a dn minus 2 and a single vertex. dn minus 2 together with a single vertex, which is just a1. Okay. So d of dn minus 1 is 4, so I get 8 minus. And then we said that if you want the determinant of 2 different graphs, then all you do is compute the first graph, the second graph, and you multiply them. This guy has determinant 4. This guy has determinant 2 by my table. And so I get 0, which is a contradiction because I should have gotten a positive number. Okay. So that proves that gamma has at most one branching point. Okay. So that's good. And let me say something a little bit stronger, which is that now I know I have at most one branching point. So if I am finite and have all edges equal to 3, then I need to look something like this. I have to have a single branching point and look something like that. But I'm actually going to discard this by proving that actually the branching point can have at most 3 branches. So gamma has no branching point with 4 branches. How do I do that? Well, I keep making the very same argument, which is to say, okay, if I did, then I would have some part of the graph that looks like this. I might have more branches, I might have more things, but I just focus on this part, and this part should be positive definite. Okay. But what's the determinant of this part? Well, again, I just peel off one of the edges, so I get 2 times the determinant of the 4 minus the determinant of what happens when I erase this edge and this vertex, and what I'm left with is 3 isolated vertices, which is called A1 cross A1 cross A1. Now d of the 4 is 4, so I get 8. Now this is d of A1 multiplied by itself 3 times, so that's 2 cubed, which is 0. So not positive, which means that you can't have something like this, which means that if you are finite and you have all edges equal to 3, then you don't even look like this, you look like this. And so you see we're almost finished. We have proved that if we're finite, then we're like this, or we're like this. And now we just have to prove that you can't be too big. Yeah? So let me give this thing a name. So if I have p vertices here and q vertices here, then I'm going to call this graph IPQ of M. And if I have P vertices here, Q vertices here, and R vertices here, then I'm going to call this graph the Y of sizes P, Q, and R. Okay. So the only finite things are of this form, and now what I have to prove is that P, Q, R, and M are not too big. So how do I do that? Well, I keep doing the same kind of argument. So for example, here, let me just tell you what are the things you need to check. You need to check that if you have, I want to basically cancel everything except for those guys, right? So for example, one thing I want to say is, if I have a number 6 or bigger, then it looks like the only thing I could possibly be is that single edge. So how do you prove that? Well, you prove that by saying, if you had something 6 or bigger and you had another edge, then this wouldn't work. And so the way you do that is you just compute this determinant by one of the several methods we have, and you find that it's less than or equal to 0. Okay. So that means that if you have something bigger than or equal to 6, then you must be I2 of m. Okay. So now we're left with things that are 5 or smaller, right? So the next thing we would like to prove is that if you have a 5, then you must be either I2 of 5, H3, or H4. Right? So how do you prove that? Well, basically by proving that, for example, that you can never have something like this. So you just prove that this group is infinite, and the way you prove it is by computing the determinant, and you find that it's less than or equal to 0. And then you do that also for this guy. You compute this guy, and you show that it's less than or equal to 0. By doing that, you have proved that if you have a 5, then you can have at most 2 things next to it. You can't have 3. And if you have a 5, you can't have things to both sides of you. And so that proves that you're either H3 or H4. So if you have a 5, then you're either H3 or H4 or I2 of 5. So now you have dealt with things that have 6s or bigger. You've dealt with things that have 5s. Now what about the 4s? Well, you need to prove that if you have a 4, then you're either Bn, F4, or I2 of 4. So how do you deal with that? Well, you want to prove that if you have a 4, then you might be arbitrarily long on one side, but you can't have more than 1 on one side and 1 on the other side. So what you do then is you show that this guy is less than or equal to 0, which means that that's an infinite Coxeter group. Okay. And when you've done that, you've shown that if you have a 4, then either you only extend to one side, in which case you are Bn, or if you extend to both sides, then you can only extend one to each side, which means that you are F4, or you don't extend at all, which means that you are I2 of 4. So now that deals with the 4s. And finally, you have to deal with when you have something like a 3. Okay? And then you have to show it basically that you can't branch too much, that you're either a straight line, or you have one long branch and 2 small branches of length 1, or these are the biggest branches you can have. So then one thing you check is basically that what we would want to call E9 is not finite. One, two, three, four, 5, 6, 7, 8, 9. Okay. So this would be what's called E9, but this one, if you compute it, you find that it has a determinant 0. Okay. And so that means that if you have one of the branches which is greater than or equal to 5, then you can't have another big branch. You must be Dn. So if one of the branches is greater than or equal to 5, then you must be 1, 1, that branch, which is just dr plus 3. Okay. And the next thing that you show is that you can't have all 3 branches be long, like this. In other words, you can't have all of P, Q, and R bigger than or equal to 2. Because you compute this and you get that this is less than or equal to 0. So you can't have this, okay? And then you just do all the possibilities, right? You say, okay, well, they can't all be greater than or equal to 2. So one of them has to be 1. Then if another one is 1, then I look like this. If another one is 2, then I can't have anything bigger than 5, so I'm going to be either, well, two or 3 or 4. Okay. This is Dn, and this is E5, E6, and E7. Okay. And then I guess you have to figure out that you can't be 1, 3, n either. Okay. Anyway, you see the point, which is just you do this analysis very carefully, and you basically show that these are the borderline cases where you go from being finite to being infinite. Okay? And I mean, again, this is the kind of classification that the best way to understand it and be completely fully convinced that you believe it is to do it yourself by going through these steps. But what you do is you show that if you're not on this list, then you contain one of these things, which means that you're infinite. And so when you're done with this analysis, you have proved this classification. So we have proved this theorem that the irreducible finite Coxeter groups are exactly the things on this list. Okay. So that proves this analysis. That concludes this analysis. And the next thing that we will discuss, we will do this in the next class, is basically see what this has to do with the classification of regular polytopes. Because somehow you want to understand, okay, so these things look like this, but what do they actually mean? For example, what does it actually mean that I have this irreducible finite Coxeter group? This is something that I can make sense of, and we'll see that, for example, the reason why this exists, or one way to see why this exists and one way to understand this group is to draw a regular icosahedron. And actually, I want to ask you to do this exercise, which is to learn how to draw a regular icosahedron. Just stare at it until you can draw it. And I know it sounds very hard at first, but you can do it. And maybe I'll ask one of you guys to draw an icosahedron at the beginning of class next time. Maybe I'll do it myself. But then we'll see why this guy is actually the group of symmetries of the icosahedron. And that's one reason to see why it's finite, is because it's the group of symmetries of this thing that has finitely many symmetries. Okay. And maybe this shouldn't be too surprising to you, because, for example, we know that this guy is the dihedral group, and the way that you learn the dihedral group defined is not by generators and relations. You learn that the dihedral group is the group of symmetries of a regular polygon. Okay. And so it shouldn't be too surprising that we can think of a lot of these groups in this way. Okay. Maybe actually Actually, let me change the exercise to something that is a bit more manageable and maybe more mathematical. Which is, I want you to think about the symmetries of the cube and understand why the symmetries of the cube are described by this diagram. And then we'll see. We'll basically see all of this next time. But it's something that really it's a lot easier to understand if you've stared at the picture for a while.
Yeah, the text has not changed, so take a look at that.
Making it look regular is going to be the hard part. Sorry, I haven't applied this to my long-term memory, but Mondays are the late office hours?
I haven't either. Let me check. I think that's right. I guess it's not worth remembering anymore. Yeah, 2.
And do you know any good references on Gorensteinness of matroid polytopes? Just off the top of your head.
You talked to Sirkin about this?
Sirkin talked to me about this. I don't know if he told me to.
Because that's all I know about it is what he and I talked about.
Okay.
I don't think anybody was thought about this. Maybe he told you that we have one. We have one matrix polytope that's Gorenstein.
And this is
And then there's
toric algebra associated to this Gorenstein, or is this?
Yeah. And
so this Gorenstein property is the property that makes the H vector and the Earhart H vector line up, right?
I honestly don't know a lot about this.
So what's your?
I remember something like that. Yeah.
There's something like that. So what's the example? Is it something nasty or?